Here's a quick introduction to torque. In the linear world, what causes the linear acceleration of a mass? Well, that's force from Newton's second law, F is equal to ma. In the rotational world, what causes a rotational acceleration, alpha, on an object with rotational inertia is called torque. Okay, so if we've got, for example, this rod, and it's going to spin in this direction because it's being held down right here by a hinge, and we apply a force to it, that force is going to apply what we call a torque onto this rod. We're going to talk about the direction of that torque being into the screen or into the page later on in class. Now, the way we calculate torque is this way. The magnitude of the torque is proportional to the product of the position vector and the component of the force perpendicular to the position vector. So this equation is a technical equation for that, but we'll learn about that in AP Physics C. This is the version of the equation we really want, where tau, that's small t, is the torque, r is the moment arm, you'll hear me call that the position vector, and F is the force. So in this particular picture here, if we apply a force, and that symbol there is called phi, that angle, if we apply a force at an angle phi, the way we would find the torque that's being applied right there on this wrench is first we've got to know the position vector. And all the position vector is the distance from the hinge, or where it's spinning around, the rotational axis right there, from that point to there. So we call that the r vector, or the moment arm, or the position vector. We take that value, we multiply it times the component of the force that is perpendicular to the position vector. So because this force is not at a 90-degree angle, this force here is not at a 90-degree angle to the position vector, we have to do a little SOHCAHTOA, and we have to find what this component is, because we only want the component that is perpendicular to this position vector. And it turns out the way we would find that out is by taking the sine of that phi angle, and multiplying it times our force. So R times F sine phi gives us the torque at that position. So in this particular question, it asks, which of these forces produces the greater torque on the rod? You'll notice that this rod is supposed to be spinning around this hinge right here. It's a 1 meter long rod. The red force and the blue force are each 5 newtons, and they're being applied to the same point. So the torque is a position vector times the component of the force perpendicular to the position vector. So let's look at the red force first. The 5 Newton force has a horizontal and a vertical component to it. The only component that we want is this vertical component. That's the component perpendicular to our position vector. So our position vector would be right along this rod. It's 1 meter long, and we want to multiply it times just this component of the force vector. So that would be 1 meter, and since that component is 3 newtons, 1 times 3 gives us 3 newton meters. That would be the value of the torque applied at that point there by that particular 5 Newton force. If we look at the other 5 Newton force, the blue 5 Newton force, it's at a different angle. So when we figure out its components, the component that's perpendicular to the 1 meter long rod is this 4 Newton meter. This 4 Newton force. It's the component that is perpendicular to this position vector right here. So when we multiply that out, we still use the same position vector, 1 meter, which is this length here, from that point to there, times 4 newtons. So we get a torque of 4 Newton meters. All right. Now, a torque can also be applied to a particle moving in a straight line as long as that torque is calculated relative to some point. So let's say this object here experiences a force of 2 newtons straight up. if we want to know what the torque is relative to the origin, there's a couple things we need. First, we need the position vector. That's easy. It's just 5 meters. Then we need the components of this 2 Newton force that will go perpendicular to that 5 meter position vector. And that's where we can use this equation. So as long as we can figure out what this angle is, so if we do a little geometry, we'll find out that's a 37-degree angle. So we want this component right here, which would be opposite that angle. So that's, again, why we're using the sine of that particular angle there. So we take the position vector, which in this case is 5 meters. We multiply it times the force that's being applied times the sine of the angle between the position vector and the force vector. And we get a total of 6 Newton meters. And in class, we will study rotational static equilibrium.